And before discussing this algorithm, we'll first see few of the basics or preliminaries which will be required in order to understand this algorithm. So how do we denote a single qubit? Any single qubit, any single state can be written as A ket 0, B times ket 1, and we can write it in the vector form like this. And the bases are ket 0 and ket 1, right? So if we apply, so yeah, so 0 is a special case of this when A is A and B are the coffee amplitude. They are called amplitude. When A is 1 and B is 0, this becomes get 0, and get 0 can be represented like this in a vector notation. Similarly, when A is 0 and B is 1, here get 1 can be represented as 0. I have briefly discussed in one of our lectures that how this hammer gate work to a qubit. So what does hammer gate do? It takes 0 state to the superposition state. Like this with equal probability and take one state as this, right? Therefore, any general qubit which has this state A0 and B1, A get 0 plus B get 1, when Hilbert cat is applied over it, we can write it like this. So this is the output, or you can call it phi. Equivalently, if you want to see the same operation using the matrix notation of H, if you know how you represent H is a unitary operator, we can represent it equivalently as a unitary matrix. And in the previous lecture, I have told you that how to find out the matrix corresponding to this H. So if this is the matrix corresponding to Hadamard gate, and this is the vector notation for the qubit state phi, if you want to know what is the output state, what you need to do, you need to multiply this to the AB, and we will get 1 by root 2 A plus B, A minus B, which is equivalent to writing as, so this is in the vector form, and in the superposition form you can write it like this: 1 by root 2 A plus B of this basis plus A minus B by root 2. This is the amplitude corresponding to basis 1, get 1. You can say that this and these are same. This we have evaluated by understanding the nature of it, right? What is the nature of it? That it converts the state to the superposition state like this, and 1 to this state, 0 minus 1 by root. You can see that 1 and 2 are equal by just applying few algebraic manipulations over it. Just take 0 common. this and from here and here, you will see that the amplitude corresponding to 0th ket 0 is this, and amplitude corresponding to ket 1 is this. So these are equivalent. So if you want to see what is the output of other merge gate to any general qubit of type A0 plus B ket 1, you have two options. If you know the what is the characteristic of H, what it does to 0th and 1, ket 0 and ket 1, you can do it like this. Or if you know the matrix corresponding to H, you can write first, you can write what is the equivalent notation of phi in vector form. You can write A ket 0 plus B ket 1. And then we can multiply this with the matrix H and we can get this. How to equivalently write Hadamard gate in form of a matrix we have already discussed in the class. So I would like to ask this question to you. What is the output of Hadamard gate? Hadamard gate is a single qubit gate. Right? Since we are discussing single qubit, this is how we denote or not how we can write this single qubit, and this is this gate which is very important gate, Hadamard gate, is a one single qubit gate. So now if my input qubit is of type this, what would be the corresponding output? What you need to do in this equation, you can write A and B, replace with A as 1 by root 2 and B with 1 by root 2. So you will get that A as 1 by root 2, B as 1 by root 2. Have I made any mistake? Let me check. A plus B by root 2, A minus B by root 2. Yes, this is right. And here 1 by root 2 minus 1 by root 2 by root 2 get 1. And if you solve it, you can easily see it will go away that the answer is get 0. So if we apply a qubit of type this, which is superposition of 0 and 1 with equal probability, and phase is also either here there is a plus sign, then we will get a get 0. We also represent this type of state as state. One of the reasons of calling it plus state might be that this state is in the superposition of 0 and 1, and adding you are just superposing the 0th and 1th state with equal probability, and we represent it by get plus 1. Get plus. So similarly, if we apply a state of 1 by root 2 get 0 minus 1 by root 2 get 1, the output of this would be, if you just replace A with 1 by root 2 and B with minus 1 by root 2, you will see, and it is not very difficult to check, that the answer would be get 1. And we also denote this or write or represent this as get minus 1. So if I summarize my results which I have done so till now, if you apply 0 to Hadamard gate, we will get, we also call it plus state. If we apply one single 1 ket 1 to the Hadamard gate, we will get ket 1 by root 2. We also represented by minus ket minus 1. If we represent or if we apply h to the plus state, we will get ket 0, and if we apply minus to this, we get, बताओ, right, 1. So these are the results which will be helpful when we study Deutsch algorithm. Further, few more things will be required. Multiple qubits. So when we have a system or a box which operates over 2 qubits. So we have 2 qubits in our disposal, and we all know that qubit can be in the superposition state. So if Q1 is in like this, A1 of ket 0, A2 of ket 1, and second qubit Qt is the superposition of 0 at 1, and the amplitude corresponding to ket 0 and ket 1 is B1 and B2. So what is the composite? What is the composite state? We see at the same time, the composite state is tensor of Q1 and Q2 state. So what is this tensor? So it would be easier to understand the tensor if we write A1 and A2 like this. I told you that we can also represent our qubit in the vector notation like this. So when we say that our phi is in the tensor of this, meaning equivalently if you write Q1 as A1, A2, that is why I am using equivalent sign. Tensor of B1 and B2 these are the bases. This is how we represent the, because Q1 is A1 times ket 0 plus A2 times ket 1. These are the trivial things which you know from your linear algebra course. This is our equivalent vector notations of the qubit Q1 and Q2. So if you apply tensor product to it, the tensor product provide you a vector in the bigger vector space rather than V1 cross V2 vector space, and 0 0 0 1 1 0 1. As you can see that this is a 2 qubit setup. This is a 2 qubit setup. So how many bases are possible? 0 0, ket 0 0, ket 0 1, ket 1 0, ket 1 1. And if you see the composite state, it will be superposition of any of these bases. Computational bases. We also call them as computational bases. We already have seen this, right? But what is the amplitude of these individual computational bases? You have to get it like that. You have to multiply A1 with B1. This is the amplitude corresponding to 0 0. So you also multiply the amplitude corresponding to 0 0. Now you want to find out the amplitude corresponding to 0 1. So you need to multiply A1 with B2. Similarly, we want to know the amplitude corresponding to 1 0. So you will get A2 B1 and A2 B2. Similarly. Our phi is can be equivalent. The composite state of a two-qubit setup is a tensor product of the first qubit and the second qubit. And tensor product can be better understood like this. That is why I have written them in the form of a vector notation like this, column vector, and then we have applied tensor product. Now you can simply write how your phi would look like. It would be A1 B1 amplitude of 0 0 plus A1 B2 of 0 1 plus A2 B1 of 1 0 and A2 B2 of 1. If you can see, it is not very difficult to see that this uh, summation of magnitude square of all these is 1. You can check it under the condition that A1 square, because we know these things from our first lecture that any qubit, the probability of occurrence of 0 is mod of A1 square and probability of occurrence of 1 is mod of A2 square. Meaning if you measure this Q1, then mod of A1 square times you will get that it is in 0 state, and mod of A2 square times you will observe that it is in 1th state. Therefore, the summation of these two probabilities must be 1, right? Because they are mutually exhaustive, right? There is no other event. So the probability must be 1, right? So under this constraint, if you apply, you can easily see that this will be equal to 1. You can do it. Right. So if we have a composite state of phi of 2-qubit setup, and if we apply a Hadamard gate to it, what will be the corresponding output state? As I told you, first you write phi as a tensor of, or like this, right? This is your so the output state is actually you are applying Hadamard to the first qubit. This phi is the Q1 tensor product of Q2, which you can equivalently write like this. And you are applying identity to the second qubit. So this you can write like this. H over Q1. So if you want to evaluate it, you can evaluate it like this. First apply H to A1 A2, then apply I to B1 B2. So nothing would happen. Have to change because identity. So apply H to A1 A2 and then take tensor product of this with B1 B2. So actually when we write our basis, our qubits like this tensor product, and we apply one single qubit operator to a single qubit, this is the way we can easily analyze this, that what would be the output. So please do it, take 2 minutes and solve it. What would be this value? You apply H over A1 A2, so you have to write H in the form of a matrix because you have written it in the form of a column vector, right? I have already told you that how to analyze the output of a H, right? H. So if you do it, 1 1 1 minus 1, A1 A2, B1 B2, and of course these bases are this. So if you further do it, you will get then you need to take the tensor product. So I told you that tensor product will give you a vector in the bigger vector space, V cross V vector space, A1 plus A2, B1, A1 plus A2, B2. This is the amplitude corresponding to the 0, 0 basis, computational basis, 0, 1, 1, 0 and 1. Right? So this is how we can write the output of the Hadamard gate. I mean, when we apply Hadamard to the first qubit and second qubit, we do nothing, right? This thing will, later on will be used for the when we see the Deutsch algorithm. So now we have covered the preliminaries or the required basics. So now we can go and see the Deutsch algorithm. So Deutsch algorithm is a way, is an algorithm which shows that the quantum algorithms are faster than the. This is I would say to example where we show that quantum algorithm is faster than the classical algorithm. So for this, the problem in hand is we have a function f which takes a single bit as input and provide a single bit as the output. Right? It's a classical digital circuit of where there is one input, and if we apply f, the input is 1, in this case 1 bit, and the output is also 1 bit. So if you want to know that whether if fx is constant or not, the problem in hand is to find out if fx is constant or not. So for this we have to make two queries. What will be the first query? When we provide x0, what is the value of f0, and when we provide x equal to 1, what is the value of f1, right? Or what is the value of f0 and what is equal to f1. So we have to do two queries, and when we compare f0 and f1, if f0 is equal to f1, of course it's constant, but if f0 is not equal to f1, it's not, right? So to two queries, right? We need two queries in order to solve this problem. This is a classical digital circuit, some digital circuit where x can be either 0 or 1, right? And the function we apply, it's a single bit digital circuit where the input can be single bit only, and we want to know if it is a constant. So we need to make two queries. What Doyce did, he actually showed that we can do the same thing, or we can solve the same problem or this problem if we have an equivalent quantum circuit of this type, which is a unitary operator operating over two qubits, and this is what it does. It takes x and y as two qubits as input and provide x and y as x. So if you write composite state of this, the composite output is like this: x tensor y. So firstly, the assumption is that there exists a unitary operator uf corresponding to the f, which is the problem in hand is to find out if f is constant or not, and if we have a corresponding uf where if we provide these two as input, we get these two qubit as input, we will get this type of output. if we have this type of UF with us, how can we solve the problem in hand using one query? So let's see this. So for this, we have to analyze this quantum circuit first, and once we analyze this, we will really appreciate the Dash way of showing that yes, quantum algorithms can perform faster than the classical ones. So for this, given this UF exists, he first provided the first input to this. I mean, we have the first qubit is the output of the Hadamard gate applied over 0. So what would be the answer? We all know that, right? So you can write first qubit, and second qubit is this, right? So this is the second qubit. So if this is your phi is 0, what is the composite state phi 1? It is a tensor product of this, right? If this is the composite state of this two qubit system, you can write the composite state as tensor product of first qubit and the second qubit. So which is like this. And we can easily solve this if we use this equivalent notation, right? This is how we can write the ket minus and ket plus respectively in the form of a vector, right? So the tensor product of this will be equal to, please speak up, right? So the tensor product will be, and the basis will be the expanded space, vector space, right? Of dimensionality 4 with this computational basis, right? So how can you write now your phi 1 as? Now you can simply see this and easily write that our phi 1 is the input to this UF unitary operator will be this. So the input to this unitary or the quantum circuit, you can say, or this operator, quantum operator or unitary operator, which applies to the two qubit setup, two qubit system, is this. So what would be the phi 2? What would be phi 2? First you see what is phi 2. Phi 2 is, it does not change the first qubit. Whatever is the first qubit, it will be the same. And the second qubit will be this, right? So if you see, the phi 2 will be this. It will not change the first qubit, and the second qubit will be y XOR or y modulo 2. It is a modulo 2 operator, y modulo 2 fx. So y modulo 2 f0, right? So if you see that if you apply modulo 2, or you can see it as an XOR also, it will not change anything, right? So whatever is f0, it will be the f0. So you can write it as a f0. So whenever the input to this uf is 0 0, you will get this. Similarly, for 0 1, you can see 0 f 0, because now this is 1 XOR with f0. So whatever is f0, because f0 can take only two values, 0 and 1. So f0 bar, because when you multiply or XOR with 1, you will get this, right? So this is the case modulo 2 operator, we all know. Similarly, all of you can check this and let me know if I am making any mistake. Hopefully, this is correct. So this is the output of this, right? Output composite state of this UF will be like this. Now let's try to see how this phi 2 would look like for two scenarios. Because what is the problem in hand? We want to know whether f0 is equal to f1 or f0 is not equal to f1, right? This is the problem in hand. So how this output composite state would look like for these two scenarios. So further you can see that these two scenarios can be bifurcated. When f0 is equal to f1, we can write both are 0 or both are 1, right? Similarly, this can be the case, right? That f0 is 0, in that case f1 will be 1. And when f0 is 1, f1 will be 0. So how this phi 2 would look like for all of these scenarios, we'll see. So let's see this. First, this scenario when phi 0 and phi 1 both are 0, at that time the output of this UF would look like this. You have to replace f0 with 0 and f1 with 0. So you can easily see just take some time and try to do it by yourself. So it will be 1 by 2 0 0 minus 0 1 plus 1 0 minus. Similarly, for this case, when this scenario occurs that f0 and f1 both are 1, the output state would look like this. You can simply replace f0 and f1 with 1 here, and you can see it's not very difficult to check this. And you will observe that this is minus of that. So phi 2 for this scenario, when f0 is equal to, can have either this or this. Plus would consider this and minus would consider this case. So if you put plus minus, it will occupy both, or it will consider both these scenarios. Now let's see this when f0 is not equal to f1 and f0 is equal to 0, right? Then f1 will be 1, and when f0 is 1, it will be 0, right? Because when f0 is 1, f1 is not equal to f0, so it must be 0. So in that case, if you follow first scenario over phi 2, so this is the case when f0 is equal to f1, we will have this. However, when f0 is not equal to f1, we will see following the first case, the output is this, which is not very difficult to get. Just you need to put f0 is equal to 0 and f1 is equal to 1. f0 is equal to 0, here you put f0 is equal to 0 and f1 is equal to 1. And similarly, this is the complement, right? Complement. And if you follow this second path, you will see that interestingly, this is the negate of or minus of this. So now we can write that when f0 is equal to f1 and when f0 is not equal to f1, right? So we will have, this covers all the possible scenarios. But still, I mean, how would you know that whether f is constant or not? Right? This is the problem we need to solve. So for that, if you rewrite this phi 2 equivalently in this form, you might get some intuition or some idea. Here I am writing this function or this qubit state in the form of a tensor product. If you see, half times 0 0, half times minus half times 0 1 plus 1 0 minus half 1 1. So just consider this, right? Okay, so this is equivalent of writing that I have plus minus ket plus multiplied with ket minus, right? Right. And if you see similarly, the second example, we will see that you can write it as this is the case that we are having 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2, which is same as plus minus ket, you need to check it, tensor product of minus. So what you see, what is our problem? That we need to know whether f0 is equal to f1 or f0 is not equal to f1. Second qubit, if you see, of phi 2 is constant in both cases, same in both cases, right? But here, this is plus and this is minus, right? Somehow, if we do something to this first qubit, we can find out, or we can differentiate between two scenarios, right? This is the, so what Deutsch did, actually, he put a Hadamard gate here and checked what is the, so what we did here, we have put a Hadamard gate to the first qubit and the second qubit we have not done anything. So what would happen for the first scenario? If you see, the plus you apply this to this scenario, we will get Hadamard applied to this conjugate with tensor product with minus, we will get, so we will get, sorry, excuse me for that, this as 0 and this will not change. So the first qubit will be in 0. You can see that the first qubit is in the computational basis state 0, while the second qubit is in 1 by root 2 0 minus 1. So it is in the computational basis. Similarly, if we apply, if you see what would happen for the second scenario at the output. So now we are observing actually this phi 2. No, sorry, phi 3. We call it phi 3, right? Phi 3. Because this is phi 2. So we are observing phi 3. So the output will be, we applied, what is this? We applied Hadamard to the first and identity to minus, which is equivalent to, when we know that when we apply Hadamard to this, right, we have seen this, correct? In our result, we will get computational basis 1. So you can observe that the first qubit is actually, if you see, in a way, XOR of F0 and F1 for this scenario, because both are equal. When they are not equal, this is the scenario where we are getting this phi 3. This is the phi 3, right? This is the phi 2, and we have applied this Hadamard and identity Hadamard to the first qubit. So in a way, our first qubit has the information about, if you measure this first qubit, if you measure it, and if it comes out as 0, if it comes out as 0, then you can say that yes, my function is constant, and when it comes out as 1, so if it is 0, we call F0 is equal to F1 or 1. Or in other words, the output will provide you F0. So in one query here, you can see that Deutsch algorithm shows that by applying only one query, we can find out whether our function was constant or not. Whereas for the classical one, we have to do it using two queries. So of course, we did it using single query, right? Therefore, the quantum algorithm, this is an toy example. We can find out, we will see, or we will study various such things, various such examples. But one very simple toy example where we can show that quantum algorithms work faster as compared to the classical ones. So I think this is it for the Deutsch algorithm. And if you have any doubt, you can ask. Right. We know, right, that when we measure, right, so this is the first qubit, right? The first qubit, if you see, with probability 1 will give you 0th computational basis, because we know when we measure any qubit, it collapses to the computational basis. And here this is the only, I mean, this qubit is in the pure computational basis, you can say, or the single computational basis, 0 only. So it will always give you 0 when you measure the first qubit. Similarly, it happens here.